Good evening. This video is about fuel systems. It's going to be a little bit of a longer video as I have a lot to cover, and so it'll be a little more edited with some cutscenes kind of thing. And I had to take a lot of notes for this one so that I could keep track of everything that I want to explain. So first, let's just talk about the basics of a fuel system. We're going to stick mostly to Subarus. They're very similar to a lot of other cars, and we'll also discuss some of the similarities and differences between the different types of fuel systems. But overall, they're really simple. There's a fuel pump. It transfers fuel from the tank via lines, be hard or soft, to the fuel rails, which then distribute the fuel to the injectors, from the rails to the pressure regulator that controls fuel pressure and then diverts the unneeded fuel back to the tank. That's a return style fuel system. There's also one called a return-less style system, and that's used on a lot of Chevys and other manufacturers. In that system, the rails are the end of the flow path. Well, the injectors technically, I guess, are the end of the flow path. And so fuel only flows in the lines when the injectors are firing. In a return style setup, as long as the fuel pump's running, the fuel is flowing. It's going pump, lines, rails, regulator, back to the tank, and it just circulates continuously along that route. In between the pump and the rails should hopefully be a fuel filter. Bigger, nicer, boutiquier injectors require better filtration in order to get a lot of flow and to have good control at small pulse widths. The injectors have to be machined very precisely, and needing or having a good filter is imperative to injector life and maintaining injector balance. So let's talk about the first part of that system, and that's fuel pumps. Fuel pumps, there's a couple types. There's in-tank and external. I have pictures of some representative ones here that are obviously many of the shapes and sizes based on what's going on. The top one there would be in-tank. The bottom would be an external inline fuel pump. And those fuel pumps can also have other traits inside them. The method by which they move fuel can be different. In a old school Warbo 255, for example, it's a gear rotor pump. It physically moves fuel via positive displacement by the difference in volume between two gears as they rotate, much like the oil pump on many cars, Subarus and the LS series and that kind of stuff. The other style is a turbine style, and the turbine styles are basically like a centrifugal pump or a propeller on a boat, or even the turbine in a jet engine, that is. So the turbine style rotate a lot faster because they're not doing positive displacement. They're not saying taking a volume of fuel and then moving along. They're not grabbing a volume of fuel and moving it. They're slinging it. They're if you've ever seen a propeller, for example, and you put a boat in the water, you can mash the throttle and the boat doesn't go anywhere instantly, right? If there's some slip there. And the turbine ones and the gears both have pros and cons to them. The gear style, being positive displacement, isn't very good for throttling flow. If you run the pump at full speed and your injector demand is really low, that means you're putting more fuel than the engine needs, and the regulator has to open a lot. And if you run a gear style pump that's bigger than the regulator can bypass effectively, then that would be what's called regulator overrun. Also, the regulators have a hard time controlling pressure to the point, to the actual PSI. And as a regulator opens more and more and more, the pressure still actually goes up a little bit. But if you overrun the regulator, it's full open, or that spring is fully compressed, and the pressure still rises because there's more fuel than the regulator can bypass. Turbine style pumps, on the other hand, they're much more forgiving in the throttling department. As pressure goes up on the discharge of the turbine pump, it requires a little more speed to push fuel. And so the demand will affect the flow rate of the pump a little bit. And that's nicer for the regulators and that kind of stuff. But the high speed of the turbine pump has another issue, and that's cavitation. If the fuel temperature gets high, and a lot of guys with DW pumps or AEM pumps that are turbine style will see this, the way they got a lot of these higher flow rates is to spin the pump even faster. And that creates a low pressure. And the low pressure happens on the suction side of the blades, if you will. And if the temperature of the fuel gets higher, with that low pressure, you can lower the pressure of the fuel below its vapor pressure, and you'll get pockets. And so what will happen is on a dyno that has limited ventilation by the fuel tank, and so the exhaust just sits there and heats up all the fuel, plus the pump is spinning the whole time, pushing fuel um, through the engine, which is hot, and back to the tank. So it just recirculates fuel, pumps adding energy, engine bay heats adding energy, everything's adding energy to the system. The fuel pressure will, or temperature will start to go up. And in a lot of these aftermarket pumps, around 130-ish degrees Fahrenheit, you'll run into cavitation. And what it'll manifest itself as a leaning fuel trend on the top end. As you're doing a pull, all of a sudden, say $5 grand or something, you'll start noticing that the AFR curve is going up towards lean. And that's usually an indication of a declining fuel pressure. And that is usually your first indication that you're having cavitation on one of those turbine style pumps. And so a lot of guys will go, oh, the pump went bad on the dyno, the pump is shitty, and they'll take it out and put another pump in, and the problem goes away. And they're like, oh, I fixed it with this pump. Well, that's not what happened. What happened was the fuel cooled off while you were doing it, and all the extra vapor that was in there now is gone. And you put a new pump in there with cooler temperatures. Hey, it works great, and you're able to finish the tune because you're almost done anyways. And you just didn't even realize that it wasn't a problem with the pump; it was actually cavitation, which is a little bit of a problem with the pump, if you know what I'm saying. So the gear pumps aren't susceptible to that. They turn slower. They don't have this really high speed turbine spinning in there, churning up the fuel and create these different types of low pressure regions inside there. And so they're not as susceptible to the cavitation that turbine style pump is. But gear style pumps are really loud. Notice that like an old school Walbro pump is way louder than a new style, like a DW300. We'll have a little mee to it, but the Walbro 255 is like there's a, I hope you like my impressions there, but the gear style pumps are louder. So, each one has pros and cons. If you can keep your fuel temperature under control, then the turbine style is great because it's easier on regulators and that kind of stuff. But then also brings me to another thing. Fuel injectors, right? Fuel injectors are, there's a ton of them on the market, right? And they meter and deliver fuel to the engine, okay? Well, there's a lot of brands, like I said, a lot of stuff on the market, a lot of good stuff, a lot of bad stuff, and they're really important. But what happens with some people don't realize is the flow rate through the fuel rail and the size of your injector is kind of important. You may have heard of the GR stumble. It's known that the GR stumble is caused by resonances in the fuel rails, but a lot of people haven't really gone so far as to figure out, why they're there. And this is my theory as to why it is. You can take it for whatever you want. I believe this to be true, and I'll explain to you why. My theory, and the reason that I believe this to be true also is that I've done some testing, a lot of testing on it, and it changes with fuel pump selection. The hesitations change with fuel pump selection. You might go, what? That's weird. So if you take a GR and you put ID1000s on it, then you run into a leaning trend, typically 25 to 3,000 RPM, somewhere in that range, at a medium load, somewhere around atmospheric pressure, sometimes a little less than that, a little more, where all of a sudden it just starts going lean and you got 25% correction, you're adding fuel to some of the compensation tables, and it's still lean, and then you got 50% fuel on it, and it's still lean, and you can't tune it out. That happens. Sometimes you can tune it out though, which is what's weird, right? Like, why is it different? On 1300s, you almost can never tune it out. Like 1300s is pretty much going to be a lean spot that you can't get out, and you can add dampers to it, and you can change the reference of the fuel pressure regulator. I've even put 2 regulators on a car before, trying to fix it. And the only thing that fixes it is putting larger rails on it. And then with the 1000s, like I said, sometimes you can tune out really well, sometimes you can't. And what's the difference? Well, what I have found is that if I put 1000s on a car with a stock fuel pump, now you might say, why would you do that? Well, sometimes people have their VF series turbo and it runs into boost creep, and they don't want to go with external wastegate setup. They just want to have the extra fuel there. So if it creeps a little bit, hey, I got the fuel there, it's not going to run lean. But if you're on stock injectors and you get boost creep at around 5,000, plus RPM, you run out of fuel. And so the cut's got to remain. But if you have bigger injectors on there and the mass airflow sensor is still in range, you can just keep adding the fuel needed for that, and it's not that big of a deal. Yeah, it's more back pressure on the engine than you probably want, but as long as your tune compensates for that, it's not a big deal. And if you have a larger injector, then hey, that's great. And since your total fuel flow is only really going to depend on your total airflow, then you don't need bigger than stock pump on a VF turbo. You just don't. What I've noticed though is that the stock pump cars with ID1000s have less hesitations. They're easier to tune out. Well, why could that be? And I thought about it for a while, and I started thinking about it. Engines operate, they run on inertia. So many things the way an engine runs on is inertia. Even the air in the intake manifold, right? Air has mass. You go on the highway, you put your hand out the window, right? You feel it blowing on your hand. It's your hand trying to accelerate the weight of that air, right? Accelerate that air. And that air has inertia, has weight, has mass, and it pushes back on you. Well, in the manifold, it's got mass too. And when the intake valve closes, right, that air that was moving now hits this closed valve and bounces back, and you get these pressure waves in the mouth. Well, fuel's no different. Fuel per volume has way more mass than air does. And so now I have, we'll say, a stock fuel rail, which has a really small diameter. And so if I have a really small diameter and a high flow rate, the fuel is moving really fast through that small diameter pipe. But a stock fuel pump has a lower fuel rate than the aftermarket pumps. And so while the fuel is still moving fast through that rail, it's not moving as fast as with an aftermarket pump. And now I have this big injector with a really small pulse width at idle or at low loads. And so I take this really fast moving fuel and I go and trigger this injector. Well, that fuel's got a lot of inertia and it's moving in one direction. And I'm trying to get it to change direction to go down into the injector. And then that change in pressure that occurs when you try and change the fuel direction creates a pulsation in the rail. And those pulsations stack up. And if you hit a certain resonance, like any tuner has seen, between 25 and 3,000, 2,500 and 3,000 RPM, you see that hesitation occur, that resonance occurs in there. Something to do with that pulse width and the speed of that fuel creates hesitation. But if I slow that fuel down through the rail, it's moving slower. I'm not changing the pressure now, right? I'm just moving it slower. Then when that injector opens, it doesn't take as much of a pressure change to move the fuel and change its direction into the injector. And therefore the pulsation, the strength of that wave that's created by the injector opening is less. And all of a sudden I find myself able to tune out the hesitation fairly easily. In fact, not nearly as aggressive as I have to be if I have a bigger pump. And then I've noticed that with raw blow pumps versus DWs in the fuel tank, that the hesitation is more likely to occur on the higher flowing pump or the gear pump. So I think, like I said, that's my theory as to why it happens. But how do you address that? Well, like I said, you can try and tune around it. But if you're in a car that doesn't have those maps available, the pressure compensation maps, you have to do something mechanically to the system to fix it. And what most people have found is the only real fix is to put aftermarket fuel rails on there with a larger internal diameter. And with a larger internal diameter, you have a slower moving fuel. And if it's moving slower, again, it takes less pressure change to make the fuel change direction. It's got less inertia. It's moving less in one direction. And to make it change direction is a lot easier. Therefore, it's going to have a smaller pulsation. Like I said, that's my theory. And those are the reasons why I believe it to be true. I think if you mold it over your head, you might find that it is probably pretty accurate. That's probably what's going on. So, moving on from cavitation and pulsations, let's talk about injectors. Injectors, again, are important. Having the proper atomization at low pulse width is really important. You know, getting an injector to flow evenly at high flow rates near their peak flow rate, that's easy. That's not a hard task. What's hard is getting an injector that flows a lot at full flow rate also to flow the correct amount at a low pulse width, at a low flow rate. And that's where some injectors set themselves apart from other injectors. I'm a huge fan of ID. They're the first manufacturer of injectors to ever measure an injector way down there at the low pulse width area. And why is that important? Well, honestly, your engine doesn't spend the whole time at full throttle. It spends most of its time idling or cruising. So wouldn't you want an injector that was balanced down there in that region? Because it ain't as easy as you think. It just isn't. And, you know, there was a time when RC Engineering was a popular injector, and they had those big body, you know, Bosch injectors, and a 550cc injector seemed like a big injector. And even then, those things were a nightmare to tune. You often couldn't even get the engine to idle at stoic evenly because one injector was flowing way more than the other at idle. Now we're running 13, 1700, 2200 cc injectors on cars at idle. And in order to do that, you got to have precision, and that's why I prefer ID for that. Again, I don't want my videos to sound like endorsements or product reviews, but that's just one of those things where, for me, it's ID or nothing with injectors. Rails. So we talked a little bit about larger rails, slowing down the rate of the fuel through the rail. That's really important. So some aftermarket rails are really small in diameter, and they don't aid in eliminating the pulsations at all. Now, there's also different ways of hooking rails up. There's been the big debate, series versus parallel. I was a big series fan. I was a series fan because Subaru did it that way, and I believed in the logic by which they used to do it. If you were to look at the firing order of a Subaru 1324, the 4 is the first injector fed by the fuel pump, right? It's the closest to the fuel pump. And so the firing order 1324 was always moving closer to the fuel pump, and I like that about the design. Cylinder 1 was the last one being fed, and it was closer to the regulator. So if for some reason cylinder 1 was a drop in pressure, or the fuel at cylinder 1 was a drop pressure, the regulator's right there to raise it up. And you were always drawing fuel away closer to the fuel pump. And it's hard to explain, but that was something that I really liked about it. The problem is that if you have small rails, when you have small rails, you have high fuel flow. And so, or high fuel speed in the rail. And so what some people do is go parallel to help with that. And if you don't know what those are, I got a picture here for you. This is an electrical circuit, but you get the idea. You see the lamps there at the top? Those are in series, which means that the electricity in this one, or fuel in your fuel system, would go from one to the next, to the next, to the next. Parallel, you can see that the fuel splits, or the electricity splits in this picture, and then feeds both of them at the same time. So at either time, neither of them should really be affected by the other one and how much fuel is drawing or electricity is drawing. Parallel is really cool. It works pretty well, and it's super common on V8s because in a V8, the firing order is not in a straight line. In the Subaru, it's in a straight line, 1324, right? That is the direction that the fuel is flowing right down the rails. And so for that reason, the series is more forgiving in a Subaru. And like I said, I like it because it means the fuel is running, the same fuel running through both rails, which helps keep the temperature the same and that kind of thing. Whereas if they're separated in parallel, then the same fuel is run through each of them, and you can have a different temperature in the fuel rails. And that was something I tested a long time ago, I think 09 actually, and I found that to be true by 15, 20 degrees, and started seeing a lot of injector issues on one thing. And so that was the reason I like to keep the fuel in series. But as injectors got bigger and as cars making more power, it's just not working out as much. So sometimes I'll go parallel. It just depends on the system. And which one's right for you? Again, that totally depends on your fuel system. If your rails are big enough in diameter, then you can go series. If series is great because it requires less hoses, less adapters, less fittings, and that kind of stuff. If your rails are small diameter and you're finding yourself dealing with issues and getting fuel to the injectors, or you're running so much horsepower that 2 injectors or 3 injectors are enough to empty the rail out, which would really be something. But then you may find that parallel works for you. And so I can't tell you which one is better. I like the simplicity of series, and there's some good reasons to use it. And there's good reasons to use parallel as well. So, like the fuel pumps, I can't tell you which one's better because it totally depends on which pro or con you're going with. Now, what happens when you are no longer able to put enough fuel pump in your gas tank? Well, the GD series and GR series for a long time were limited to one fuel pump tank. And then there were some companies made a dual pump hanger, but the fitment was really poor. There was no surge tank capability. The wiring was a nightmare. They were prone to leaks. Hooking it up mechanically, hooking up the fuel lines, everything was just required a lot of modification to the car. And so a lot of people would go with a surge tank. And the way a surge tank works, here's some there. You'll see in the center, I got the actual fuel pump hanger. So one of those intake pumps would fit inside that basket there. And that would go in the fuel tank. And it would be stuck with one in the factory pump or factory tank. Then on the right, I got the radium set up there. That's the radium triple fuel pump setup. That's a surge tank that you can mount almost anywhere in your car as long as you have room for it. That's a pretty big basket. And it can fit anywhere from 1 to 3 pumps in it. Some guys put 3 Walbro 450s in it, or just 2 or whatever. And then the other one you'll see is just a standard fabricated swirl pot style surge tank. So how does that system work? Well, you see in the diagram there, you got the fuel tank, and the main fuel pump in the fuel tank, preferably one, sometimes two if you run a lot of fuel, pumps fuel from the tank to the surge tank. Now, what's cool about this is that fuel pumps flow more at lower pressures. So what happens is if you have the surge tank at a very low pressure, which is what usually happens, 10, 20 psi or so, then that fuel pump is able to flow near its peak rated value instead of flowing way less at your higher boost pressure levels. And to show that, I have this for you here. So here's a chart. I went away. Here's a chart that shows you fuel flow to the bottom there, or so that's pressure, and the flow is the y-axis, and you see the graph. So you see you have a decline in fuel flow as pressure increases. So let's say your base pressure is 43.5 psi, and you can see that, oh hey, at 13.5 volts, at 43.5 psi, I get right around 400-ish liters per hour of flow. But then as boost increases, fuel system pressure also increases, usually a 1-to-1 scale on most cars. And so if you ran 20 pounds of boost, now you're at 63.5. And you can see, looking at that chart, if you follow it up, it's around 340 liters per hour. So you've lost 60 liters per hour in flow rate because you've raised the pressure. Now, say you run 30 pounds. Well, now it's way lower, right? Now you're at 300-ish liters per hour. So you're losing, a quarter of what the fuel pump is rated at. And then you go over 90, you see a lot of pumps tank. Some tank at 100, some tank at 90. But it's usually around that point you start seeing significant drop-offs, in flow. And so if you're running a high horsepower car, you may find yourself in need of 2 fuel pumps. It's because the fuel pressure drops so much, or the fuel flow drops so much as pressure increases that you actually need 2 of them. You're no longer getting 450 out of the pump. You're getting 300 or 280, or in this case 250 if you're at a 90 psi fuel pressure. So what you can do to help with that is you get a surge tank, put 2 pumps in it. But you only need 1 in the tank because the 1 in the tank is staying up at the 450 mark. And sure, at full throttle, you will draw more fuel into the engine than that single pump can provide. But that surge tank has a volume there. And so with that volume, you have time. You couldn't do a nonstop throttle pull for 5 minutes if you never let out of it because you drain the tank and eventually run out of fuel in the engine. But people who race let off the throttle. You shift gears. You slow down for a corner. All those times when you reduce the fuel demand, the primary pump is able to refill that surge tank and keep it going. Obviously, it's important to make sure you have enough fuel flow and you don't drain the tank. But what you find is that now I have this 450 pump. It's always doing 450 because I'm only pumping it at 20 psi into a tank or 10 psi in a tank. And I only need those other 2 when I'm in boost at full throttle. So that's a really good thing for somebody. If you find that you can't fit enough fuel pump in your tank, then you get a surge tank. You get a surge tank, and then just put a nice big one in the fuel tank, the biggest you can fit in the fuel tank, and usually it's enough to keep the surge tank full for most situations. So now that surge tank is filled. Like I said, it's low pressure. You have 1, 2, 3 pumps in it that are larger, flow more, and then those will feed the engine. The return flow from the engine goes back into the surge tank, and so at all times you're trying to keep that surge tank full. The overflow from the surge tank goes back to the fuel tank. So what happens is, even when the fuel tank is going down, the surge tank is always staying full. The primary pump in the tank is keeping the surge tank full, and then the return flow from rails again, back in the tank, hopefully keeping it full. How big of a tank do you need? Again, that totally depends. If you find that you can't put a big enough pump in the tank and you need more reserve capacity, then you need more. You need a bigger tank. If you need to put more fuel pumps in there, you need a bigger tank to fit the pumps. The more pumps you have in there, the quicker you can empty that tank. So the tank size is important based on your fuel demand. And you can do some math and calculate what it's going to be. You're going to need to know the actual flow rate of your fuel pump and the pressures you're going to use, what your peak boost is going to be, see how much fuel you get out of the pump, compare that to your injector size at 100% duty cycle, provided you even hit 100% duty cycle on your engine, and then back calculate from there how big of a pump you need. And then if you have a difference in the supply of your primary one to your secondary one, you find that difference in flow rate and you can calculate how much reserve time you have in the surge tank if you were to never let off. How many seconds do I have before I would have to let off or shift or slow down for a corner? And you'd be surprised to find out that it's not as big of a tank as you might need. Now the one in the picture there on the left, in that swirl pot design, you see that the returns and the supply are off to the side, and that is just to help the fuel separate from the air bubbles and also not generate a lot of air bubbles by jet streaming a bunch of fuel into a stationary liquid. You see aeration happen when you squirt water into a glass. For example, if you were to put the glass up there and still hit it, you'd still see bubbles and stuff form because the water's coming in there at a high rate of speed. And so the swirl pot helps to keep the liquid sticking to the side and let the air bubbles escape out and not get all of the fuel in the surge tank polluted and aerated and that kind of stuff. One of the last things I want to talk about is just the fuel types. Pump gas, E85, just ethanol, various percentages of ethanol based on what's federally mandated or where you buy it from. Methanol, propane. There's lots of different ways that you can run an engine. And your injector size will depend on which fuel you're running. Gasoline, race gas and gasoline, typically has a stoichiometric value of 14.7, maybe down to 14.1 based on the ethanol concentration of it. And what that means is you need 14.7 parts of air per 1 part of fuel. But then you get into the ethanol blends, and the ethanol blends can go all the way down to 8 to 1. That means that you need 8 times as much air as you need fuel. What that means really is if your cylinder volume is the same, you need that much more fuel to meet that ratio demand. And so if you're trying to run a flex fuel system, you need injectors that are large enough to satisfy the increased fuel demands on ethanol, but also small enough that if you're on full pump gas, they can actually modulate the injector properly at those low pulse widths and get the fuel balance to the cylinders. And so it's really important that you don't go too big on injectors, because if you care about idle and cruise and that kind of stuff, and you need to run full pump fuel, then you're going to find in a lot of cases 17s are even too big. And some cars are different, but if you have a bigger cam, then that means that the intake valve closes later in the compression stroke, which means really your engine displacement is less at idle, and so you need even less fuel in the engine, which means that a big cam car will be harder to get to idle on 700cc injectors than a small cam car. Only a little bit, because it creates only so much engine torque to keep the engine running at that RPM. But you will find that to be the case. It's a pretty interesting phenomenon. And so with that, another reason why I prefer a specific random injector, because they do a better job of regulating fuel flow at those low rates. I talked earlier a little bit about fuel pressure regulator overrun, and that's where the fuel pump has more flow than the regulator can bypass, and that results in an increase in fuel pressure. Even if you don't experience overrun, I also mentioned that as the valve opens to control pressure, that pressure still goes up some because the spring is going to compress, it's going to stack, and you're going to get a rising fuel pressure regardless with bypass rate. And that's where fuel speed controllers, fuel pump speed controllers come in handy. You can adjust the fuel pump speed with duty cycle so that the regulator doesn't get too overrun and you don't have issues with fuel pressure changing. However, if you're on a regulator with a really small disc, which is the actual sealing surface in it, or you are using so much pump, the regulator is having a really hard time. But that means you're having a really dynamic range, a really wide range in how much that disc has to open and shut. And if that's the case, then your pressure is going to oscillate a lot with changes in fuel pump speed. And so a very often overlooked upgrade is a nice fuel pressure regulator. The aeromotive one is really common. The 13109 is a common regulator that's used, and that's good. But sometimes you need a little more. Sometimes the aeromotive by itself just isn't enough, and that's where you got to go to the next size up aeromotive, where they have the larger disc and seat. And so if you go through their website, you can find the ones for fuel injected boost referenced systems with higher, with larger seats. Other people also make regulators. For Innovations, again, I mentioned them when I was talking about fuel filters. They make one that I like a lot. It has a bigger seat in it, and I find that it does a really good job of controlling pressure. So don't overlook your regulator. Don't rely on the fuel pump controller, especially as you get more and more pumps added to a system. It's hard to get a control that can handle the current associated with the larger pumps, and so a lot of people end up bypassing the controller and running the pump 100% power all the time anyways. And so for that, you definitely need a regulator that's able to bypass the fuel flow and preferably not be struggling or near the end of its range when you're at peak fuel flow. Because when those injectors start pulling fuel out of that regulator starts to shut, that spring relaxes some and your pressure's going to drop too. So it's really important to find a regulator that's large enough, it's not struggling to hold back the fuel, nothing too large where it can't maintain pressure at the low flow rates. So please go larger. If you're running more than one fuel pump or if you're running a single 450, there's nothing wrong with going with a regulator that has a larger disc or ball based on what kind of seat it is in the regulator. It's beneficial for sure, and it's something that's often overlooked. What's also really cool is a lot of those have bungs in them, and they're usually 1/8 inch MPT. If they have multiple ports, more than you need for your fuel rails or feed, you can also tap into those with an adapter that goes from like a dash 10 to 1/8 inch MPT or whatever, and you can put fuel pressure sensors in it, fuel temperature sensors. Works really good with the Cobb flex fuel setup or any aftermarket EMS that uses a fuel pressure compensation. You can put that right in the regulator and add fuel compensation tables so that if your pressure is less than target, which would mean you're not getting as much fuel as you should be getting, then it'll see that the difference pressure across the injector is low, and it'll add in extra pulse width to the injectors to try and make up for it. Now, if you're just at the end of your fuel pump's capacity, well, increasing the duty cycle on the injector is just going to lower the fuel pressure. If it's a situation where the regulator's using too much of its range and it's not controlling the pressure well enough as things change, well, that's awesome because that fuel pressure compensation could then just for that. What you can also do, and what I do on a lot of cars, if the fuel pressure gets too high or too low outside of a certain band, I have it just cut fuel. If the fuel pressure becomes 30 psi less or 20 psi less than target, then it's adding pulse width to it, and the pressure drops below that threshold, and that tells me that the pump can't keep up. And the best way to save the motor then is just go negative 100 on the pulse width on the injectors so that it turns off those cylinders. It's not lean, there's no fuel in it. If it's just air, then you can really protect it. So what happens is the fuel pressure compensation tables look like a Z. You have a 0 that it pops up to adding a lot of fuel, then dips down to when the pressure's high and it's pulling fuel, and then you get to a point where you can either just put it at 0, leave it there, so that on both ends it's that, or you can try and do it another direction with it, add a bunch of fuel, whenever you want. I prefer just go to 0 and save the motor. That's just a little pro tip for you there. The last thing I want to say before I end the video is I want to emphasize again that you should have a good fuel filter for modern high flow injectors. In a Subaru, the stock filter is inadequate. It is not enough for the higher flowing injector dynamics injectors if you want them to stay precise. They will get damaged from debris getting past the filter over time, and you will lose cylinder to cylinder consistency in your fueling. So getting an aftermarket filter like the ID filter that you see being manufactured up here in that video, For Innovations makes a good one as well, where you can choose a glass mat filter material or a stainless filter material, gets you down to a pretty low micron level of filtration, so very good filtration. I prefer the 10 micron glass mat filter personally. But yeah, so the ID one's really good. The For Innovation one are both really good filters. And it's really important if you want your injectors to last that you put something on there that's better than the OEM system, because it isn't good enough. A lot of people have injector problems down the road 10, 20,000 miles, and then get mad at the injector company and say, oh, these injectors are crap. And ID and other companies are like, well, honestly, you just didn't put a good filter on there. You got to keep material out of the injectors if you want them to last. So if you're running an aftermarket injector and it flows more than 550 cc's or whatever, you really need to put a better filter system on the fuel system. Otherwise, you'll just buy injectors over and over. I'm really excited for ID. They're doing a fuel pump setup as well as that new filter that they made. You see the display there on the left side of the screen. That is their brushless DC fuel pump flowing 670 liters per hour. I think it's running 43 psi, in that video, and that is a lot of fuel. And it does a really good job as you crank the pressure up and maintaining really close to that flow rate. It's really amazing setup. I can't wait for them to finish it. It does require a big controller that's the size of an amplifier, for a car stereo, but it's really something, and I think that it'll change the fuel pump setups in the market. And the last thing on fuel pumps, I mentioned getting them in the tank. Radium has a new setup that fits in the GRs and fits 2 pumps, and it has a little bit of a surge tank idea behind it, and that's also a really good setup. So now, if you have the need for something that flows more than a single AM320 or DW300 or whatever, you can run 2 320s in the tank with that dual radium hanger setup, and that's really cool. I think they're making one for the GD as well. So that's a really good solution. Minimizes the need for having a surge tank. Surge tanks take up space. They can be in the trunk of the car, they can be bolted inside the transmission, they can be in the engine bay. Somewhere you're running wires, running more fuel lines, and dealing with a lot of that stuff. And if it's not a track car, if it's a daily driver, or even just a weekend car, you might not even need any surge tank element. You're not hanging high G turns sustained for any period of time. You're not racing with a quart tank of gas or whatever. You don't need the surge tank. And so it's nice to be able to fit fuel pumps in the tank themselves and not need a bunch of extra stuff somewhere in the car. So if you got any questions about fuel systems, I hope this helps some. I know that some of it's very generic and vague, and I can't tell you, definitely run this, definitely run those, these components when it comes to fuel pumps and, regulators and that kind of stuff. But if you have any questions, feel free to ask in the comments. If it turns out to need a really long explanation, then I will end up making another video. If it's something I can type out really quick, I'll answer. Also, you can always send me an email at dominic@GetaDomTune.com. So again, like, dislike, subscribe, tell me to screw off, whatever. I'm here for you guys regardless. I'm going to keep making these videos. And this one was done at the request of somebody else. So if you have a video that you'd like to have me make, then feel free to request one, and I will do it. Again, unless it's strictly product reviews. I don't like doing just product reviews. I will happily do it, for you guys, as long as I can answer the question. If it's something I don't know, I'm not going to pretend I know it. So thanks again for watching, and have a good night.